All right, in this video for the AP Statistics test, we're going to start reviewing confidence intervals. So what exactly do you need to know about confidence intervals for the AP Stats test? You definitely need to know how to construct one based on a sample statistic. That can either be for a sample mean or a sample proportion. You also need to know how to construct a confidence interval based on the difference, whether that difference be between two sample proportions or two sample means. You definitely need to know how to interpret a confidence interval. That's really important. That comes up a lot on multiple choice. You also need to know how to explain the level of confidence. So when we talk about being 95% confident, what does that actually mean? A lot of kids accidentally think it's a probability. It is not a probability. And also we need to make sure we understand how we could actually use confidence intervals to draw conclusions about significance. All right, let's jump right into it. So let's make sure we truly understand what a confidence interval is for. A confidence interval for a population parameter based on a sample statistic is very easy to understand. First, we want to estimate a population mean, mu, or a population proportion, p. So always think about the fact that we're using a confidence interval to try to find the true population parameter, which is a mean mu or a proportion p. Now to do this, the first thing we need is to take a sample. That's either a sample mean x bar or a sample proportion p hat. Then we simply have to calculate how many standard deviations we are willing to reach up and down of hopes of capturing the true population mean or proportion. So confidence intervals are directly based on sampling distributions, which there was a video about. Highly recommend watching that video first, actually. So what we do is we think about the fact that if we think about all possible samples, that's what a sampling distribution shows, the results of all possible samples. And we certainly expect the truth, whether it be a mean or a proportion, to be in the center. And we understand that some samples could be a little higher and some samples could be a little bit lower. So if we were to grab one of those random samples, like right here, maybe this is our x bar or our p hat, but notice, because of variability, that is not matching up exactly with what's true. But if we cast an interval around that sample by going up a little bit, I'm sorry, that would be down a little bit, and up a little bit, we created interval from here to here. And notice that the truth did get caught in that interval. And as long as we get one of the many samples that are very close to the truth, when we build that interval around it, we should contain the truth. So how do you actually calculate a confidence interval? Well, the first thing is you start off with this very generic formula. It is a sample statistic, whether that be x bar or p hat. And from that sample statistic, you go up and down, plus and minus, what we call the margin of error. Now this entire back part is the margin of error. It is the critical value multiplied by the standard deviation of the statistic. The critical value is a z star or a t star based on how confident the question asks us to be. We'll talk more about that in a second. The standard deviation of the statistic is what we learned back with sampling distributions. If you're working with proportions, the standard deviation of the statistic is p times 1 minus p divided by n with a giant square root around it. If you're working with means, it is the standard deviation of the population divided by the square root of your sample size n. Now remember, those two formulas allow us to understand what I was trying to show you up in this picture here, that samples naturally are allowed to vary a little bit. So we're using that natural variation to create this interval because we're saying, hey, listen, our sample statistic isn't 100% accurate. But if we go up a little bit or down a little bit because of natural variation, we should capture the truth. Just keep in mind it's a four-step process. This is how I teach it. Other teachers may teach it differently, but I teach 4 steps. Step 1 is to always identify what it is you're trying to find. I'm trying to estimate the true population proportion of boys who wear glasses. I'm trying to estimate the true mean amount of time a high schooler takes to get to school in the morning. Always identify what you're trying to find. Second step is to check the conditions. Now, the first two conditions are always the same. The sample must have been collected randomly to avoid bias. The second condition is that your sample must be under 10% of the population to assume independence. Because typically when we sample, we do not replace. So when I go and grab a person out of the population to sample, I don't put them back, right? I already selected them. I don't want them to be selected again. So as long as our sample size is under 10% of the population, any small change that not replacing could cause is negligible. The third condition is what changes. The third condition in general is that the sample must be big enough. Now, if you're working with proportions, big enough means that your sample must contain within it 10 successes or more and 10 or more failures. If you're working with means, the big enough condition actually could take on 3 different options. Option number 1, if your population is already known to be normal, then your sampling distribution is guaranteed to be normal. So any sample size, even small samples of size 4 or 3, are big enough. If your sample is 30 or larger, then the central limit theorem can help you, because even if the population is unknown or non-normal, the central limit theorem says that the sampling distribution will still be normal as long as your sample is 30 or larger. The final scenario is if your sample is under 30 and you do not know that your population is normal. Here, you simply need to take a quick look at your data to make sure that there's no major skewness or no major outliers in it. After checking all those conditions, the third step to a confidence interval is all the work that I'm about to show you. It's actually building the interval using this formula that I just went through. After that, you need to interpret your interval. You need to explain what that interval represents, and it's very simple to do that. You're simply saying, I'm 95% confident that the true population blank, filled in with the context of the problem, is between this value and this value. Okay? And we'll go over that as well. All right, let's move on to talking about the critical value, the Z star or T star. Obviously, this value is needed anytime you're building a confidence interval. It is entirely based on how confident you want to be. If you want to be 95% confident, or 90% confident, or 99% confident, this value will change. Well, all you have to do is think about how far you're willing to reach. Obviously, if I want to be 99% confident, I need to reach out a little bit wider, so my interval is going to be bigger. If I only want to be 90% confident, then my interval can actually be a little bit smaller because I don't have to reach out as wide. So first off, anytime you're working with proportions, you need to use Z star. So how do you find Z star? How do you find your critical value for a specific level of confidence? Well, the first option is using your calculator. Second, VARS, and pull up invert norm. Invert norm will help you find your critical Z star. But you have to be very careful what to enter in. First, you asked for the area. This is the area at the very, very bottom. So you have to process this. If I want to be 95% confident, that means that there's 95% in the middle. That means that 5% is being left out. But because of symmetry, that 5% gets split evenly. 2.5% at the bottom and 2.5% at the top. And that is what the area wants, the bottom. So I'm going to type in 0.025 because for 95% confident, that would put 2.5% at the bottom. Kind of a little bit tricky that this is how invert norm works, but sorry, that's how it works. So your Z star is 1.96. It does say negative because we looked at the bottom, but remember, you're going up and down. So technically, your Z star is positive or negative. So to repeat this process for 90% confident. 90% confident puts 5% at the bottom, and it also puts 5% at the top because 90% in the middle, 10% left out, 5% on each end, and invert norm only wants the bottom end. So 1.6449. One more time for 99% confident, you have to put in 0.005 because if you're 99% confident, that means 1% is left out, and that is split evenly, 0.5% on the bottom and 0.5% at the top, and the 0.5% at the bottom is what we want. So we get a Z star of 2.5758. Now these are the three most common levels of confidence. If you were asked about a weirder level like 96 or 98%, then you just have to process it through the way I just explained. All right, how do you get a T star? Anytime you're working with means, you need a T star. So anytime a problem is concerning with population means, you need a T star. So how do you get a T star? Well, once again, right underneath invert norm is invert T. This will help you calculate T stars. It also asks for the area at the bottom. So if you're 95% confident, once again, that'll put 0.025 or 2.5% at the bottom. Now the other thing it asks for is your degrees of freedom. Remember, the T models are all based on how many degrees of freedom you have. Kind of a weird name, but simply degrees of freedom is your sample size minus 1. So you are required to know how big your sample is. So let's just say we have a sample of 40. Well, then that would give us 39 degrees of freedom, and our T star for 95% confident, 39 degrees of freedom from a sample size of 40 would give us a T star of 2.0227. Now keep in mind it does say negative, but remember it's actually positive and negative. Now another way to get your Z stars or your T stars is to use a T-chart. A T-chart is provided to you on the back of the AP statistics test, or it's attached to the formula sheets and all that stuff. So you don't have to use this if you totally understand how to use the calculator. Some kids actually like a T-chart better. So let me show you one. Here's an example of the exact T-chart you will be given on the AP Stats test. It says T distribution critical values. So what you do on the left-hand side is you look up your degrees of freedom, and you could look up your tail probability, that's the area at the bottom across the top, or if you scroll to the bottom, you'll notice it actually has the level of confidence. For example, 95% confident, which has a tail probability of 0.025, as we mentioned. Then all you got to do is match that up with your degrees of freedom. So let's just say you have a sample size of 16, that gives you 15 degrees of freedom. You follow the 15 over to the 95% confidence column, and you have 2.131 as your T star. So a lot of kids like this just because they don't have to waste their time typing things in the calculator. They could just simply look up their T star. Now, this actually also has Z stars on it, but they don't tell you that. The bottom row is identified with an infinity. Now remember, the T model is just like the normal model for really, really big samples. So for a sample that's infinite in size, that's essentially going to be the Z model, or Z stars. So if you look across the bottom row, those are your Z stars. For example, 95% confidence, you may remember we found 1.96. For 90% confidence, we were 1.645. Actually, we said 1.6449, but they only round to 3 decimals here. 99% confident would be the 2.576. So that bottom row there is your Z stars. So instead of using your calculator, you are more than welcome to look up your critical values on that T-chart. All right, the last thing I want to mention before we move on is, what does the level of confidence mean, since we're on the topic? So when we say that we're 95% confident, what does that really mean? First and foremost, it's not a probability. Most kids think that means, oh, there's a 95% chance that the truth is in our interval. Not at all. That is not at all what it represents. It represents the fact that you have to understand that we built our interval based on our one sample. We went a little bit above it, we went a little bit below it. But if somebody found another sample, they might have a slightly different interval. Or another sample, a slightly different interval. Or another sample, a slightly different interval. So what 95% confident is actually talking about, it's talking about the fact that there are many, many, many samples out there. Tons of samples out there, just like yours, of the same size from the same population. If you think about all those samples, the idea is that 95% of those samples will create intervals that contain the truth. So it's not about 95% probability or 95% chance or even 95% of the time. It's about 95% of intervals. 95% of intervals created just like yours will contain the truth. It goes back to that picture I drew earlier. We know that according to a sampling distribution, the true mean is smack dab in the middle. So as long as we get a sample near it, when we build that interval, we capture it. So as long as we are one of those many samples that are near the truth, our interval should capture it. And the idea when we say we're 95% confident is that 95% of those intervals do contain the truth. Obviously, there is that chance that we get an interval down here, a sample down here, or up here. Now, those would be really unlikely samples, and their intervals would not contain the truth. But that's the remaining 5%. So 95% of intervals will contain the truth, 5% will not. That's what the level of confidence means. All right, let's talk more specifically now about estimating a population proportion. So let's say we want to find the true proportion of all boys in high school that wear glasses. All right, that's what I'm trying to find. How am I going to do it? Well, the first thing I'm going to do is I'm going to start with a sample proportion. Maybe I found in a sample that 32% of boys wear glasses. Okay, that's my sample proportion. From there, I'm going to go up and down by my margin of error, which is a combination of your critical value, the Z star that we just talked about finding, based on how confident you are, times the standard deviation of the statistic. And this is where we run into a slight problem. The standard deviation of a sample proportion is the square root of P times 1 minus P divided by the sample size n. The problem is, I don't know what the true P is. Remember, that's what we're trying to estimate. So I can't possibly calculate the standard deviation of the sample proportion if I don't know the truth. So we do something better. We use, well, I take that back. Not necessarily something better, but we use an estimate. We use something called standard error. Standard error is very similar to standard deviation in every aspect, but it's simply an estimate. So since we cannot use standard deviation because we don't know the true P, standard error, good news, is the exact same formula, but instead of using P, it uses P hat, because we do know P hat. That's obviously our sample proportion. So to calculate or to estimate a population proportion with an interval, we start off with our sample proportion P hat. We go up and down by Z star, that's our critical value, times the standard error. And to calculate the standard error, we use this formula right here, which is the same formula as standard deviation, but because we don't know the true P, we have to use P hat. Easy. All right, what about estimating a population mean? What if I want to know the true average time it takes a high schooler to get to school in the morning? What is the true mean? Well, what I can do is I could take a sample mean. Maybe my sample mean shows that the average of a group of 40 kids is 10.3 minutes. Great. So now I'm going to take that mean from my sample and I'm going to go up and down by a critical value, which we just got done talking about is a T star based on your level of confidence, times, once again, the standard deviation of the sample mean. So what's the formula for the standard deviation of the sample mean? Well, it is sigma, the standard deviation of the entire population, divided by the square root of your sample size n. But wait a minute. I don't know the standard deviation of the entire population. Heck, I don't even know the mean of the entire population. That's what I'm trying to estimate. So how could I possibly know the standard deviation of the entire population? Well, we don't. You're absolutely correct. So what I'm going to have to use is something called standard error once again. Standard error is just like standard deviation in every way, but instead of using the standard deviation of the population on top, it uses S. That is the standard deviation from our sample divided by the square root of n. So again, instead of using sigma, we use S, the standard deviation of our sample, because I know my sample, for crying out loud, and I'm going to use that as an estimate for the standard deviation. And that is where we get standard error from. So that is how simple it is to estimate a population mean. All right, what about trying to estimate the difference between two population proportions? For example, what if I want to know, hey, I wonder, is there a difference, or what is the difference between the proportion of boys that wear glasses and the proportion of girls that wear glasses? What could the difference be? Well, I have to first start off with the difference between two samples. So I'm going to take a sample of the boys minus the proportion from a sample of girls. So I have to first use my sample proportions, right? Now, obviously I gave you a specific problem with boys and girls, but if I want to keep things very generic, I would just be 1 and 2, right? The sample 1 versus sample 2, looking at the difference between them. So I'm going to calculate my difference between my sample proportions. Then once again, I'm going to go up and down by a margin of error to build my interval. I once again need my critical value, Z star, based on how confident I would like to be, times, well, once again, I would like to use standard deviation, but I can't. I have to use standard error. Now, the only issue now is that I have 2 proportions, not 1. So what is the formula for standard error? Well, it's a little bit of a different formula, but if you pay attention in class, I explained where it came from. It's a giant square root. You're going to do p hat 1 times the opposite of p hat 1 divided by the sample size for group 1 plus p hat 2 times 1 minus p hat 2, all divided by the sample size for group 2. And combining all of that together, that gets your standard error for the difference. So it's kind of a weird formula, but we did talk about where it came from, and I don't want to get into it too much in class. We're basically combining the 2 together, and it is p hat 1 times the opposite 1 minus p hat 1 divided by sample size plus p hat 2 times 1 minus p hat 2 divided by sample size, and then a giant square root around all that. Do all that together, that calculates your standard error. You can find your interval. Very, very easy. All right, one more to go here. Estimating the difference between 2 population means. So, is there a difference between how long it takes a boy to get to school and the average amount of time it takes a girl to get to school? What's the difference? Well, the first thing I do is got to look at some samples. I'm going to look at a sample of boys, and I'm going to look at the difference between the sample of boys and the sample of girls. Now, I could use a B and a G here, but I'm going to use a 1 and 2 to keep it generic. Basically, I have 2 samples, and I'm going to look at the difference between them. Now, that's the difference between my samples. That's not necessarily the difference between the true values. So what I'm going to do is I'm going to go up and down by a margin of error in hopes of locating what that true difference could be. I need a T star because when you work with means, you need T star. We talked about how to find that critical value already. Times, once again, a standard error. Okay, I have 2 samples though, so what's the standard error for 2 samples? Well, it's kind of, again, a weird formula, but here it is. It's a giant square root. It's the standard deviation from your first group squared divided by the sample size of your first group plus the standard deviation squared of your second group divided by the sample size of your second group. So again, it's a giant square root. Inside of that square root is the standard deviation of group 1 squared divided by sample size plus the standard deviation of group 2 squared divided by sample size. That will help calculate the standard error you need to build that interval. And it's really that easy. All right, let's take a look at a couple examples. That way we can make sure we know how to actually use these intervals. So, a 98% confidence interval for the population mean amount of time for a high school student to get to school in the morning is 8.3 to 18.7. So what does this interval mean? Let's interpret this interval. The first thing I have to start off with is saying I'm 98% confident. I'm 98% confident what? Okay, use the problem, right? I'm 98% confident that the true population mean amount of time for high school to get to school is somewhere in the interval between 8.3 minutes and 18.7 minutes. So I don't know exactly what the true average amount of time it takes a high school to get to school is, but based on my sample, it's somewhere in that interval. I'm 98% confident it's in that interval. All right, what is my point estimate? That's oftentimes a multiple choice question, maybe even an FRQ. If you have the interval, what was the sample mean? Well, remember how an interval is created. You take your sample mean and you go up and down by the margin of error. That should put the sample mean smack dab in the middle. So all you have to do to find that sample mean is add together 8.3 and 18.7 and then divide by 2. The dead center will be your sample mean. That means my sample mean must have been 13.5 minutes. That was the mean of my sample, and then I calculated my margin of error. By the way, we could also find our margin of error because all I got to do is take the 18.7 and subtract the center. Sorry about that mistake there. And that gives me a margin of error of 5.2, or I could take the bottom, 8.3, and subtract away the center. And that would give me the same margin of error, but negative, because again, you go up and down. So my margin of error would be plus or minus 5.2 minutes. All right, let's make sure we once again, because this is really important, so I'm going over it twice, is what does 98% confident means? Well, this was my interval. If people were to conduct more samples of the same size from the same population, every sample mean would technically create its own interval. Now, 98% of intervals will contain the true population mean. I just hope that mine is one of them. So it's not about a probability. Again, the truth is either in my interval or it's not. But I'm 98% confident that it's in my interval because I know that 98% of intervals, just like mine, will contain the truth. All right, let's look at this example. Now, this often comes up on the AP Stats test, and I want to make sure I'm very clear on this. I've seen this statement worded many times, and I want to make sure everybody understands it. So let's go back to our interval, 8.3 to 18.7. This is a statement that's often I've seen on multiple choice. It'll say something like this. If the true mean was outside our interval, then the probability of getting our sample mean would be very low. Okay, that's a great statement, but a lot of kids don't understand why. Well, here's the deal. We're 98% confident that the truth is somewhere in this interval. So all I'm trying to say is that if the truth was not in that interval, let's just say the truth was 20 minutes. Obviously, my sample did not contain it. All that means is that my sample mean of 13.5 must have been very, very significantly low. That is why the interval around it did not contain the truth. It all comes back to that sampling distribution. If 20 minutes really is the truth, then my interval should have contained 20 minutes. But the fact that my interval didn't means I must have had a sample way down here that when I built my interval, I missed the truth. All that tells me is that my sample mean was a very unlikely sample. Now, unlikely samples do happen. Unfortunately, mine's one of them. And again, this is why we say we're only 98% confident that the truth is in our interval. But it does bring up a good point that if the true mean was outside of our interval, then the probability of getting our sample would have been very low. But again, we don't necessarily believe in low probability events occurring. That is why, again, we're very confident that the truth is not 20 minutes and that it really is in our interval. All right, let's do another example now with proportions this time. In an attempt to estimate the proportion of households in his city that own at least one dog, Mark constructed the following 95% confidence interval. His interval is 0.15 to 0.27. All right, let's interpret this interval. I'm 95% confident that the true proportion of households in his city that own at least one dog is somewhere between 15% and 27%. All right, now a very popular question, often on multiple choice, sometimes on free response, is, hey, if you know your interval, what was your sample size? This is a great question. All right, this is going to take me a minute to explain, but I need a lot of information first. The first thing I need is my sample proportion, which again should be smack dab in the center. So once again, if I go to my calculator, if I take the 0.15 plus 0.27, add them together, divide by 2, that gets my sample to be 0.21. Okay. The other thing I need is my margin of error. My margin of error is how much I go up and down from my sample. If my sample was 0.21, then I must have went up and down by 0.06, because if you go up 0.06, you get 27%, down 0.06, you get 15%. All right, so what was my sample size? Now there's one more thing I need, and that is my z-star. And we know if you're 95% confident, you could simply look it up. 95% confident, your z-star would be 1.96. Or you can use your calculator. Okay, now I'm all ready to go. Remember that the back part is your z-star times the standard error. That back part to the formula is your margin of error. So now I'm just going to fill in all the blanks. The margin of error is 0.06. The z-star is 1.96. The formula for standard error is the square root of p hat, 0.21, times 1 minus p hat, which would be 0.79, all divided by the sample size. And that is what I don't know. That is what I have to solve for. So I needed the margin of error. I needed the z star. I needed my p hat so I could find my 1 minus p hat as well. And now I could solve for n. First step is to divide both sides by the 1.96. Second step is to get rid of the square root by squaring both sides. That cancels out the square root, so I get 0.06 divided by 1.96 squared equals 0.21 times 0.79 divided by n. Next step would be to, instead of dividing by n, to multiply that n up to here. And then the final step would be to divide by all of that stuff in parentheses. So I'm going to take the 0.21 times 0.79 and divide by the 0.06 divided by 1.96 all squared. Okay, so that's a lot. Hopefully you're good at algebra. This is about as hard as the algebra gets. So 0.21 times 0.79. Okay, there's that. And I'm going to divide that by, in parentheses, 0.06 divided by 1.96, and then don't forget to make sure that square is on the outside those parentheses. So I get a sample of about 177.03. I highly recommend always rounding up because that will make you a little bit more accurate. Remember, bigger samples always better. So I would say approximately 178 households must have been his sample size. That's a very popular question. Hopefully you remember how to do that. All right. Let's do the last topic, which was making sure you can understand how a confidence interval can help us understand significance tests. A 95% confidence interval for the difference between the proportion of teenage girls that wear glasses and the proportion of teenage boys that wear glasses is negative 0.08 to 0.04. So let's make sure we know how to interpret this. I'm 95% confident that the true difference between the proportion of boys and girls that wear glasses is anywhere from negative 8% to positive 4%. That means girls are 8% higher to 4% lower than boys. Or I can look at that the other way around. Boys are 8% lower to 4% higher. The fact that this interval is negative on one side and positive on the other means that girls could be 8% more than boys in terms of wearing glasses, or girls could be 4% less than boys because I'm doing I'm doing girls minus boys. So you got to make sure you truly understand how this interval works. Now, does this interval show that there is a significant difference between boys and girls? Well, no, it doesn't. Because this interval actually leads me to three conclusions. Girls could be more likely to wear glasses. Boys could be more likely to wear glasses. Or, you know what number's in this interval? A big fat 0. There can actually be no difference between boys and girls in wearing glasses. So the proportion of boys that wear glasses and the proportion of girls that wear glasses can actually be exactly the same. And if that's true, there's no difference. And that is a legitimate possibility since 0 falls in this interval. So is there really a difference? No. The interval contains 0 and the interval contains a positive and negative numbers. So do girls wear more? Is there a larger proportion of girls that wear glasses or a larger proportion of boys that wear glasses? I don't know. It could be larger for girls, it could be larger for boys, or you know what, guys? There probably is no difference whatsoever. So when we think about a significance test, which there's a separate video for, our null is that I almost drew something wrong there. The proportion of boys is equal to the proportion of girls, and the alternative would be something like, no, the proportion of boys is more than the proportion of girls who wear glasses. Well, my interval doesn't tell me that. It doesn't say that boys is more. It says boys could be more, but boys could be less, or there could be no difference. So that is when we would actually fail to reject the null, because I don't have enough evidence to say there really is a difference, because there could be no difference. So hopefully your teacher went over that with you, and hopefully that actually makes sense to you, because a confidence interval oftentimes should always support a significance test. All right, guys, that was a long video, but there is an awful lot to talk about when it comes to confidence intervals, so hopefully this will help you ace any questions on the test that cover them.